So we were doing path integral formalism, and we started off with the simplest and historically most relevant context, which was that of the evolution of the wave function, so quantum dynamics. However, even during the last few lectures, we immediately realized that a path integral formalism breeds several immediately evident applications. For instance, it allows to map a problem of quantum dynamics in imaginary time to a statistical mechanical problems of a polymer, something that has very difficult to guess without having a hand on the path integral formulation. So it's something really unexpected. But most importantly, during these lectures, the forthcoming lectures will be focusing on yet another connection that is absolutely fascinating, at least it is for me, and it has been so much insightful in the last, say, 2 decades. And it has to do with the fact that the path integral formulation can be used in an entirely classical context, classical physics context, to study dynamics of open systems. So what is an open system? An open system is a system in contact with, for instance, a reservoir. So it can exchange particles or only energy or momentum with the system. So, for instance, when you're dealing with statistical mechanics at fixed temperature, typically you are in contact with a heat bath. Now, if I bath in Garda Lake, the temperature of my body is going to adapt to the temperature of the lake in equilibrium condition. Of course, I'm out of equilibrium, hopefully. But if you drop a dead body, so to say, in the Garda Lake, then of course it will ultimately reach the temperature of the Garda Lake, while the temperature of the Garda Lake will not alter its temperature, while the Garda Lake itself will not alter its temperature significantly. So this is a prototype of open system, but rather than be focusing on the equilibrium properties of the thermodynamics of open systems, we will be interested in the dynamics. And at least at the beginning of this course, we'll be interested in the classical dynamics. So when you're dealing with open systems and you're interested in the classical dynamics, you immediately have to reckon with a fact that is not present in closed systems. Namely, since your system exchanges momentum and energies and angular momentum, whatever, any dynamical quantities with the environment, then of course all conservation laws are no longer satisfied. But most importantly, you must give up the concept of determinism. And why is that? Well, from a very, very intuitive perspective, think about it this term. Let's take a very clear example of a molecule, of a system of an open system. Let's take a molecule, let alone in water. So you have a collection of atoms in water. Each and every atom on their molecule is going to be subject with interaction with the surrounding H2O molecules. Right, so you have your molecule in water, I don't know, maybe it's a polymer or whatever it is. And all around it, you have these H2O molecules, and I'm drawing them as little dipole, whatever they are. And they hit the atoms. They have their own velocity, so all they basically do is provide thermal agitation. And by providing thermal agitation, they can either absorb energy from your atoms, they can get kicked by the atoms and absorb energy, or they can inject energy into your system. Now, under normal conditions, I expect the amount of energy that flows from the system to environment to be equal to the amount of energy that flows from the environment to the system. Otherwise, the system would either blow up or freeze. right? So for the system to be reaching equilibrium, for the system to be able to reach equilibrium, you need to have an equal balance of energy flowing out and energy flowing in. There are exceptions. For instance, take bacteria, right? Bacteria swim in their environment, but they burn ATP. And so therefore, they do not conserve energy. They burn fuel. And it's like if they had a rocket and they keep on moving subject to fluctuations and dissipation, but what they do, they mostly dissipate and burn. So basically, if you have too many particles just flowing like that in a glass of water, they will heat up the system by dissipation, while remaining at the same temperature because they burn fuel, so to say, in order to do that. Okay, so atoms don't do that. Atoms, they have a much more basic type of dynamics. And so as far as this discussion is concerned, we will be focusing with systems that ultimately are bound to reach thermal equilibrium. So for which there is a detailed balance in the flow, in the energy flow from the system to the environment and from the environment to the system. An important thing to realize is that as soon as you dealing with open system, then immediately two fundamental phenomena begin to occur. And I want to throw the phenomenology there before we go into the mathematics, because I want to first set up what is the challenge of what we want to understand, and then build up right the amount of math that we need in order to do that. Okay, so there are two striking phenomena that occur. First is the loss of determinism. So the moment you are in an environment that you can interact with the environment, ultimately, if you are blind to the environment and only able to resolve the system, then you will see that the system is subject to stochastic fluctuations. Now, the system as the universe intended as a system plus environment, of course, in principle obeys deterministic laws. For instance, in this, we are assuming Hamiltonian dynamics for a closed system. But if you're blind to the environment and you only can resolve with your eyes the system, then you will see stochastic behavior. The most renowned one is probably Brownian motion. So Brownian motion, are you all familiar with Brownian motion and what it is and what it is implying? So basically, you can experiment Brownian motion in everyday's life by taking a glass of water with some powder in it, and and looking it against the light, through the light, and you will see that this particle have agitation. And this is an example, a prototype or paradigmatic prototype, I would say, of what is most generally known as stochastic dynamics or stochastic behavior. I would call it stochastic dynamics. So even though our underlying physical setting is entirely classical, we lose the possibility of predicting a trajectory. The notion of individual trajectories loses much of its significance, because observing a specific trajectories, after all, is basically equivalent to observing a specific sequence of random events, while out of the pool of potentially infinitely many possible random events that could have occurred. So yes, of course, you can still draw a posteriori probabilistic analysis and say this event is more likely than another. This way of this dynamics is more likely to occur than others. But once you have introduced the concept of being open, basically the notion of predictive trajectories is weakened, and you're left with predicting the evolution of probability density. So just to be clear, when we learn statistical mechanics, basically we stand on this basic idea of Hamiltonian dynamics and phase space. So when we are in phase space, we have one of the fundamental results of classical mechanics is that trajectories in phase space never cross, right? That's basically Cauchy's theorem. For every single point in phase space, there is only one and only one trajectory. This is the phase space of PQ, right? Because if you had two, then you would have a problem with two possible solutions for a second order differential equation with two initial conditions, which you obviously cannot have because of Cauchy theorem. So dynamics in phase space in classical mechanics is normally formulated in terms of trajectories in phase space. For instance, we're all familiar with the harmonic oscillator, which, for instance, this could be a trajectory by an harmonic oscillator. Or, dynamic systems, they have attractors and all sorts of things. But okay, fine. Now, the moment you are in an open system, this concept of predictability is gone forever. What you're left with is a probability density in phase space. And in the following, I often will use a compact notation for a point. I will use sometimes Q, sometimes X for configurations, and I will sometimes use this compact notation to denote a point in phase space. Now, really, your interest is in the evolution of the probability density distribution starting from some initial distribution. And this evolution obeys what is known as the Liouville equation, which I will very, very, very schematically denote in the following form, where L is the Liouville's operator. I will not bother writing the Liouville operator, but this is just. If you have done statistical mechanics, you will recognize this equation. If you have not done statistical mechanics, you don't need to be able to recognize this equation because we will never touch on that. I'm just going to start from something you might have heard of. So the goal is really this now. It sounds familiar, doesn't it? It sounds a little bit like quantum mechanics. After all, in quantum mechanics, we have to give up the notion of individual trajectories. And after we have given up the notion of individual trajectories, we are left with understanding the evolution of probability amplitudes from which we ultimately evaluate probabilities. And in fact, this is basically the reason why Einstein never believed in quantum mechanics as a fundamental theory. Einstein was the person who in 1905 solved the puzzle of Brownian motion. Back in 1905, it looks like yesterday in terms of history of science, yet you have to imagine that in 1905, people were not even completely sure that matter was discrete in essence. There were atoms and molecules there. People have, of course, discussed about their existence, but a fundamental proof was lacking. And Einstein, by explaining Brownian motion in terms of stochastic dynamics induced by molecules, he was able to provide predictions, Einstein's law, It was quantitatively understood, and therefore that was the ultimate proof of the molecular nature of fluids, right? So, but that's why Einstein always thought that quantum mechanics was due to missing variables. He thought the stochastic nature of quantum mechanics must be due to the equivalent of water molecules in the Brownian motion, some hidden variables we are not able to see that basically are coupled to my system and provide stochasticity. So he was thinking, so to say, he was taking this analogy very seriously. Seriously, the problem is that this, stochastic behavior, simply stochastic behavior, would not account for intrinsically quantum phenomena such as tunneling, or even more so Bell inequalities, coherence, and everything that has to do with phases, basically. So interference and all that. But at least you understand why Einstein never believed in quantum mechanics. God doesn't play dice, which means there must be a larger formulation of my dynamics which is completely predictive, completely deterministic. But of course, that was a statement, a metaphysical statement. It was his own personal philosophical thinking that was driving him into thinking that nature must be deterministic in essence, ultimately. Okay, so that's the first thing that happens when you open the system. At the classical level, there's at least one more striking phenomena which sets in, that is time invariance, time reversal invariance, gets broken. Time develops an arrow. So basically, you're familiar with this. I give you a perfect sphere or a perfect harmonic oscillator in vacuum, an ideal one. My system is entirely isolated and it will oscillate forever. So if I take any number of pictures and I ask you to put them into order, in temporal order, you will not be able to conclusively do that, because you cannot tell that this position comes after that on the other, right? Because it could be on the next swing of the pendulum or whatever. Or simply, you cannot simply predict that the process wouldn't occur on reverse, simply in the reverser. However, if I take my ball now, my basketball, or if I take a typical example is I fire a match and I watch it burn, then obviously you can tell what event came first and what event comes after. Now, here comes the big question for you. If I write, let's assume my Hamiltonian, let's look at the burning match experiment, right? Or even a simpler, but let's stick to that. That is chemistry. Chemistry is electromagnetism, electrodynamics. The Hamiltonian for electrodynamics is time reversible, meaning that it is left unchanged by flipping the time from negative to positive. Similarly, Newton's equations are time invariant, or even, Schrodinger equations, if you account, correctly for the Hamiltonian being time independent, they lead to reversible dynamics. So if my fundamental theory is time reversal invariant, how come I observe the emergence of an arrow of time? Do you get the question? So it means that at some level, time reversal gets broken. And in a very systematic way, not in a random way. Stated differently, if you take a magnet, an Ising magnet, and for instance, and you cool it, 50% of the time you will get a magnet polarized upwards, and 50% of the time the magnet will be polarized downwards, right? Because there's no reason why the theory, if you zero magnetic field externally, of course. While the arrow always gets broken in the same direction. So do you know why is that? Have you ever thought about that? How come if your Hamiltonian is time invariant, I get a definite arrow direction? There's a keyword which answers this question. I want to hear it.
Because of entropy.
Entropy is the keyword. Good. Ah, my pen is died again. Let's see if I have another one for a moment. Here, I have 3 pens because apparently my kid likes to kill Apple pens. So I buy them and then they start working again as soon as I buy a new one. But anyway, yes, I use my finger as far as my pen will recharge. Entropy is the buzzword. So what happens? It happens that while the total balance of energy from the fact that you have a coupling between the system and the bath has infinitely many degrees of freedom, or many degrees of freedom, makes it unlikely for energy that is initially localized in the system to come back in the same identical configuration and to be channeled back from the environment to the system at any possible finite time. So in principle, the dynamics is always time conserving, but the chances that all of the environment collectively decides to cooperate in such a way to give back the energy to the system in a specific place and time is exponentially 0. So to visualize this, let's think about the experiment when you drop a basketball, you make a couple of pulses, and then it eventually stops. The energy, the potential energy, initial potential energy still is in the room, provided you have isolated the environment. But what you're lacking is that very rare fluctuation for which all the molecules in the room decided to have a random direction of kick to the ball, all together from bottom to up, rather than in random location, giving back the energy to the ball that starts bouncing again. The moment you see that, you think the devil is in the room rather than the entropy is being violated. So much we are acquitted to entropy, growth in our education. There's ultimately a third phenomenon that sets in when you have open system, which is not evident at the classical level, and it's evident only at the quantum level. So I leave it as a side mark. We might be able to focus on it at the end of the course, and this is called decoherence or dephasing. Quantum coherence of your systems, so the fact that you can write your system as a single wave function at some initial time. So a coherent system is a system whose density metrics can be written in terms of a single state. So you can basically find a rotation in which your system is well described by a wave function. Now, when you have an open system, you cannot do that anymore, and you need to invoke the concept of density metrics of amplitudes, right? And the amount of coherence is, of course, how many states can be visited at different probability in your systems. And in order to, and when you have an open environment, because of this stochastic fluctuation, ultimately, if you are initially quantum coherent, you deplete this coherence in time. Now, this has important practical implications because it turns out to be one of the main limiting factors for the development of quantum computers, to be able to control the quality of the quantum coherent states they have over time. Okay. Now, what we want to do is to build one of the main goals of this course, if you want, is to build a theoretical framework that is able to explain and sort of rationalize and quantify and basically provides the statistical physics of all these phenomena. And why do we want to do that? First of all, for fundamental cultural reasons, so understanding how time emerges and why do we age ultimately from the physics perspective is an important question to be asking, but also for practical reasons, because this is the starting point to understand many complex systems that evolve with time in a very defined way. Take glasses, for instance, and all irreversible dynamics in general. And as a general, since most systems, I would say all systems are ultimately coupled systems. In the world, any subset of the universe is subject to irreversible dynamics on a very long-term scale. So this is not the exceptions, to be honest, is the rule. You can use, microcanonical energy conserving descriptions to study, say, atoms, nuclei, simply because you're interested on time scales and energy scales for which this dissipation effect with the environment are negligible. But if you're interested in the big picture, none of the systems, physical system in Earth is per se an isolated systems, and all that matters is irreversible dynamics. Okay. Okay, so what we will be doing today is to begin our journey into this world, and we will be doing that, and we will ultimately be able to construct different approaches, and we will discover that the natural formalism to describe these dynamics is that of path integrals once again. And maybe it's not surprising, because if you're interested in the probability for a particle undergoing, say, Brownian motion to end up in a specific place after some time, and you're subject to fluctuation, then you must necessarily account for the fact that a particle can get any sequence of random hit from the environment. So you have to sum over all possible events, each one with its own probability, to understand what is the probability for a particle to end up at a given distance or in another distance as a function of time. Okay, so, and we will see that path integrals that we develop for quantum mechanics, not surprisingly, will turn out the quite natural tool to describe stochastic processes as well. Okay, and today we get started with all this, and we will now focus on the process on a theoretical framework that goes under the name of Moritz-Zwanzig projection. And this is basically a way through which you can demonstrate how, starting from Hamiltonian dynamics, you end up with stochastic dynamics. Now, Moritz-Zwanzig projection formalism it dates back to the late 60s. I think it's 68, not sure 100%. Could be 68. And if you read the literature or the textbook of Moritz-Zwanzig, it's a fairly abstract formalism, beautifully elegant, but very little transparent from the point of view of physics. In this course, I will take a slightly different approach and will be more physical, because I think it is important you to understand in a specific case what happens, and then it will be basically a matter of it's just a matter of going through more complicated math, slightly more complicated math, not particularly more complicated if you come from a quantum mechanical formalism, because it's a formalism of projectors on Hilbert space and all that. And it will be just a matter of using this mathematical formalism if you want to go from the abstract, from the specific case to the most general abstract case. But as a result, people in practical applications forget most of the time this very abstract, and they only retain the final results, which you can achieve from the specific approach that I'm going today. So that's a lot of words. What do I mean particularly? That I will consider a specific case in which I have my system, which can be anything, but I will model the environment. But since I'm not interested in the specific details of the environment, but only interested in the details of the system, I will choose one specific model for the environment, which is admittedly not the most general. And I will consider the environment is made by an infinite collection of harmonic oscillator of different frequency, all coupled to the system. This model is well known in the literature and is a paradigmatic model for open classical and quantum systems. And it's called the Caldera-Legged model. So today we are bouncing on our third Nobel Prize winning concept of the course. The first one being Feynman's idea of path integrals, and which ultimately led to QED, and then of course Feynman's Nobel Prize. The second one, was there a second one? Ah, yeah, the concept by Wilson renormalization group, although we didn't really touch on Wilson's technical renormalization group transformation so far. We'll do it at the end of the course. And the third is, I think Legged was not ever granted a Nobel Prize at some point. I'm quite sure. I'm not sure if it was for this though. I don't think so. Anyway, okay, so let's start with our model. Our model is defined by Hamiltonian. And now, without loss of generality, let me define my system as made by a single degree of freedom. This is the part where you don't care. Generalization to multiple degrees of freedom, even possibly interacting among themselves, is trivial. All you have to do is to send your one-dimensional X into a multidimensional X, and things will run through. Okay? So there's no reason to add these complicancies at this level. We'll leave it there. But of course, if I have only this Hamiltonian, the dynamics will be Newton's law for particle X, right? Nothing particularly interesting. So we need to add more. And then I add a collection of harmonic oscillators. So let me do it here. I will write sum over alpha. These are my harmonic oscillators. These are the momentum of the harmonic oscillators. These are the masses of the harmonic oscillators. I have my masses, frequencies, or let me go to the next line. I've got my masses, frequencies. These are the position of my harmonic oscillators. And I will linearly couple these positions to my position. So let me use, oh shit. So you see, I have red variables that are concerning the bath. There are n of them, which ultimately n will go to infinity. And I have black variables that are my systems. And there's one of them. And if I solve the square, if I expand the square, I will get a terms that is a standard harmonic oscillator terms. I will get an harmonic oscillator terms for my particle, which was not there originally, and I have to deal with it, and we'll focus on that later. Okay. I can always take it off from here. You see? I can add an additional term here that cancels exactly with this, so that I'm sure that I'm not adding any dynamics, but I don't need to do that at this level because, you know, in the end, this is simply telling me that my system is oscillating around QA, because this will sort of form the equilibrium position of variable A, or Q is oscillating around X. And then, of course, I have my coupling, which is on the form QAX, right? Of course, there's a sum, there's a 2, and there's all the coefficients you want in front of that. So I'm coupling each of my variable. In this case, I have only one variable, but I'm coupling my variable to infinitely many degrees of freedom, or n in this case. Now, you might say, I want to use this model to describe the motion of an atom in water. The water is certainly by no means made of any harmonic oscillator, right? So why should this model be any relevant at all? Well, if you were to make this objection, you would be completely fair and right in claiming that. However, the big point I want to raise here is that we will further make additional approximation. And in particular, we are interested in situations in which, guess what? We are interested only in the dynamic of the system, and we assume the dynamic of the system will be slow, and the dynamics of the bath of the environment will be fast. And what is slow and what is fast, of course, we will have to specify it quantitatively later when we start writing formulas. But once again, the idea is I'm not interested in any quantum system, because remember, if my system has dynamics at all scales, it's very difficult to do any modeling because I need to take care of any possible detail. But here I'm introducing my most significant, RG based simplification, which is that of decoupling timescales. Now, as you can imagine, as soon as the system becomes slow compared to fast dynamics, all the dynamics, the details of the fast dynamics becomes irrelevant for the sake of describing the slow dynamics. We learned that from the renormalization of the Schrodinger equation, right? So basically, all details of the fast dynamics can be hidden into a few effective parameters. Affecting the slow dynamics. So as long as the details are irrelevant, I might as well choose almost any model for the ultraviolet, because all I'm interested in is how this high energy ultraviolet dynamics percolates at low energy, what kind of low energy effective theory it produces. Okay. Now, to be completely technical, I use the adverb almost because I must make sure that my specific microscopic model falls in the same equivalent class of the system I'm interested to study. That is, I don't want an effective theory which generates a completely fast, if for instance, if my underlying model for the ultraviolet dynamics I'm using, in this case, the Caldera-Largetts, violates some fundamental principles that the true systems has, then of course the resulting low energy dynamics will be completely different. So, I don't have complete arbitrariness in defining the microscopic model, but it turns out that this harmonic oscillator model is powerful and general enough to breed basically all the kind of considerations we might be interested in doing for all practical purposes, at least in this course and far beyond this course. And I think this is a fairly good stopping point for a 5-minute break before we dive into calculations. Okay, so I will gather with you, say at 5:20 sharp. Okay.
Okay.
Yes.
Ok. Puntuale come la morte, ricomincio. So that's enough for basic introduction. Now let's dig into the calculation. So the first thing we want to do, so let me just give you the idea. We're going to write down Hamilton's equation for the systems and variables, and for the entire system, the universe, say, made by the system and the environment. And then we're going to capitalize on the fact that the environment is a harmonic oscillator. Therefore, we can solve the dynamics of this environment for an arbitrary system's configurations. And we use this information to channel this solution into the equations of motion of the system. And we will analyze that under certain conditions that basically match the one that we just discussed here, the decoupling that I was mentioning, the new equations of motion become unpredictable and they basically resemble stochastic dynamics. Okay, that's the That's the overall idea. So let's start. It's a very fairly well-defined plan. All we need to do is to basically go through it. Okay, we begin by writing down Newton's equation. So it's got like x dot p over m. That's the simplest one as usual. I got my p dot negative d by dx of u of x. Then of course I've got my terms that come from the coupling with the bath, which I'll write here in the following explicit form. But then, of course, in addition to that, I've got my equation for the bath, and I write those. This is going to be p alpha divided by mu alpha, of course. And of course, I'm going to get p dot alpha. That's the Newton's equation for the harmonic oscillators. That's going to be standard Newton equations, plus the terms that comes from coupling with the system, which I write as before with black. Please stop me if anything that I say or do doesn't make sense to you. So clearly, the two most important equations in here are these Newton's equations. These are the core of the calculation, while the other two equations are simply definitions of momenta in terms of velocity, if you want, or relationship between velocity and momentum. So let's focus on the solution of the second equation, this one. First of all, we look at this. You can use the first one, the first Hamilton's equation, and write this as a q double dot a alpha. That's really Newton's equation. Now I think it's divided by, so I can use mu alpha. That's really Newton's equation at this point, right? And let me make some room here for this. So mu alpha. Now, it's a second order differential equation, which contains an unknown function of t, which is the position that for each time x of t is going to change, right? This is the notion of having coupled differential equations. Now, normally, when you have coupled differential equation, you're doomed, because to solve the second, you need to know the solution of the first, and to solve the first, you need the solution of the second. But this is one of those exceptions. Basically, the exception is due to the fact that we have to deal with an harmonic oscillator. Okay? In fact, to solve for this, all we need to do, according to the standard theory of differential equations, we need the solution of the homogeneous, a general solution of the homogeneous, plus a special solution of the inhomogeneous equation. So what do I mean? Just to refresh some concepts from your background, this is an inhomogeneous second order differential equation. And the fact that it is inhomogeneous comes from this term here. So in general, when you have a solution of an inhomogeneous second order differential equation, what you need to do is to take the general solution, the most general solution of the inhomogeneous equation, and add one particular solution of the inhomogeneous. Sorry, the general solution of the homogeneous plus one particular solution of the inhomogeneous. Did you do this in your analysis or your calculus background? Okay, fine. So I don't need to deepen this very much. Okay, so the general solution of the inhomogeneous equation is the general solution of a simple harmonic oscillator problem. That's about one of the first problems you actually see in physics, right? And you know the solutions are sines and cosines, right? So you have it, your general solution. I'm going to write in red because this is the red part of the equation. It's going to be some a sine with is, Let's start with cosine actually. Plus some b sine of omega alpha t minus t naught. And then a and b are fixed by the initial conditions, right? So if you know the initial position and velocity, you can determine a and b. And in fact, you can altogether replace them with the value that you get by fixing the initial condition. Since you know the initial position and momentum, you can actually write the following equation. And then you discover immediately that, when t goes to t naught, the sign disappears and the cosine gets to 1, and you get q alpha equals to q alpha at t naught, which is what you want, the initial condition. And if you want to know the initial velocity, you take the derivative, which turns sines into cosine, and then you tend the t to t naught, in which case you get precisely the initial momentum. The initial velocity is the initial momentum divided by the mass, which again is very obvious. So, okay, we solved the first task. Now we need a solution to the inhomogeneous equation. This looks like a very difficult problem because this is a solution which involves now the seemingly unknown solution for the systems dynamics. However, to solve for the inhomogeneous equation, we perform Fourier transform. So we do the same trick that we did over and over when dealing with Green's functions and propagator. Remember the Coulombic example we discussed last time. You want to discuss the Laplace equation, then you go to Fourier space, and then you anti-Fourier back, right? And by doing this, you capitalize on the fact that derivatives become polynomials in Fourier space. Okay? You guys are all familiar with Fourier transforms at some level of understanding. Okay? So let's do that. If I do Fourier transform, I get omega alpha square. Sorry, I go back to my red equations. Get minus omega square mu alpha q tilde of q alpha of omega. This is the Fourier frequency. Actually, it's not a frequency, it's a pulsation. Who cares? Right, we understand that. The Fourier variable. Okay. Equals negative mu alpha. Now I have q alpha. You see, omega alpha. This is a variable. Sorry, this is a parameter, not a variable. Why this is a variable, right? Because this is the Fourier. So let's not mess them up. And then I have q alpha tilde of omega. And then I get a plus C alpha, and now I'm going to switch color to black, and the Fourier transform of the position of my systems variable. Okay? And now, I want to emphasize, I could now all I can do is I can move this term on the other side and factorize out my solution, omega tilde alpha, right? So in the end, what I get is omega tilde alpha of omega is equal to C alpha divided by mu alpha, omega square alpha minus omega square, and then I get a x tilde of omega. So me? Can you hear me? Can you hear me?
Yes.
Yes.
Okay. Sorry, because I got a message that my mic went down. Okay, so it looks like magic. We have done this over and over. Anytime you have a propagator or anytime you have a Green's function, you do exactly the same thing. And that's how you propagate forward in time, basically. It's the only way. And not surprisingly, you know the propagator for the Klein-Gordon theory or for Laplace Poisson equations. They're all quadratic in the derivatives and they're all linear equations. Okay, just as much as harmonic oscillator. There's nothing really magic. But now you see I can Fourier transform back and get my Q alpha of t is the convolution of a kernel or propagator and position of my system, right? So basically I can write the following thing. Q of alpha is C alpha over mu alpha integral from T naught to infinity of d tau k of t negative tau x of tau, where k is defined as the Fourier transform, the anti-Fourier transform, sorry. Okay, we need to stop a comment on a few terms that I did not yet comment. So the first thing you see, the appearance of this guy here, I epsilon here. Okay. This term here is there to enforce causality. Okay, so I guess you might have seen this if you come from my energy physics background already when you define the Klein-Gordon propagator, but this is something that is supposed to be self-contained. So let me give you an explanation why in this anti-Fourier transform this term jumps in. Okay, well, the problem is that what you're dealing with is an integral that is in principle divergent, because you see, when you integrate this frequency from minus infinity to infinity, your omega will hit this singularity here. Now, if you hit the singularity, it means that this integral is divergent. Necessarily, not necessarily. It could be convergent in some dimensions, but it becomes divergent in other dimensions. And since the concept is more general than the particular dimensionality of your problem, you have to have a general solution, which is independent on the specific dimensionality of your integral, right? So what do you do with the fact that we hit the dimensionality? You say, okay, I cannot define, strictly speaking, this this function per se. When I integrate from minus infinity to infinity, this is my frequency plane. And when I get close to my singularity, I need to tell you, I need to go around the singularity, which will perturb the result of the integral by a finite amount, depending on what is the size of this. Now, the whole idea is that you first, that this problem, of course, if you look at this function alone, the numerical value of this function will change depending on, first of all, if you change from going about in one direction or in another, but it will also change depending on the size of this little circle that you introduce to not to hit the singularities. Of course, it's a mathematical trick. Your result will depend on that. Now, there are general situations and general conditions for which this dependency is lost when K is not looked at in isolation, but is used inside integrals, like in this case. So under general conditions, which I'm not going to lay out in details, this is for those who are interested in understanding this, they have their mathematical methods for physics, where all these conditions are laid down quite extensively, but there are general conditions under which the result becomes independent on epsilon after you have done the integral of k with something else. So in other words, in technical terms, k is not a function, is not defined in a unique way as a function, but is defined in a unique way as a distribution, something that makes sense inside an integral. Okay, you guys know what distributions are if you come from physics. If you don't, all you need to know is that you introduce these prescriptions and you hope that by introducing this prescription, your results will not change, will be independent in the limit on which epsilon becomes small, of course. On the detail of these prescriptions, when after you have done the limit after you've done your integration, the result will be independent on the choice of epsilon, provided epsilon is sufficiently small. Okay, now this discussion concerns how large epsilon should be. However, if you choose to go around the singularity in one direction or in another, the ultimate results will effectively be changed, because you see, and now I need some understanding of complex analysis. Basically, if I go around the pole and I close the contour in the complex plane in this direction, I will include the singularity. But if I go around the pole and close in the other direction, I will not include the singularity. And you might know, if you come from physics, then you can evaluate the integral around this closed contour or the integral around this closed contour using a theorem that is called the Residuous theorem. Federica, have you ever seen this? No, right?
Yes, I
Oh,
did
you have.
complex analysis.
Oh, very good. Then I was making it a long story in order to keep you on track, but if you have, fine. So Residuous theorem will give you a different answer whether you're closing one direction and in the other, right? It will count the amount of residues you have inside. I don't ask if the physicists have done it, because they must have, right? Fine. Okay, so you're a mathematician, Federica, right? Ah, I forgot. I always thought you were no, fine. So you probably are. So I was worried I was giving too much math, but actually I'm probably giving too little math. Okay, fine. So given residue theorem, now the fact is, if I close in one prescriptions, I get 0. If I close in the other prescriptions, I get a finite result, which ultimately reflects on the fact that I can always have if the time gets an arrow, because if t changes sign, the only non-negative contribution comes from the opposite pole, right? So basically, by putting this there, I've decided that the whatever systems configuration, by putting a plus here, I'm physically determining that whatever physical configuration the system has at time t naught can only affect the variable, the Bath variable, at a later time. I cannot, the fact that it's like to say the fact that I married my wife should not upset my previous girlfriend, but in fact it does anyway. So this is not probably a good example, but you understand the thing. Something that happens now cannot affect something that happens in the past, right? So this reflects in the fact, this is why I put a particular convention here, plus. Had I chosen to put my negative, I would have exactly the specular situation where only the future can affect the past. Now, unless you have antimatter, in which you have both, I mean, matter flows in both directions and blah, blah, blah. In non-relativistic dynamics, there's never a choice whether time should go forward or backwards. Should always go forward. Fine. So all this discussion is concerning a plus in this distribution value here. And now that I refresh myself on the fact that we have all strong mathematical background, I'll be able to be a little bit faster in my mathematics. And I apologize for having been a little bit pedantic, thinking that I was hoping to keeping people on track, okay? And Federica, to be honest with you, you told me about that. I just forgot. It's a sign of aging. Okay, so you can do this integral. And it's nice to do it with a residue theorem. I don't want to do it explicitly. It's a trivial exercise. The result is a theta function with with a term like this. This is causality again. And I think this is plus now, and it goes here. This plus comes from here. Okay? So, going back, my complete solution reads sum of the inhomogeneous and the homogeneous. So Q alpha T naught cosine omega alpha T negative T naught plus P alpha T naught over mu alpha sine omega alpha T negative T naught. And then plus integral, oh, well, I put the sum C alpha mu alpha, sorry, yes, omega alpha integral square T naught T d tau, or sometimes I use tau, sometimes I use S. Well, I use tau, x of tau sine of omega alpha T minus T naught. And here I'm using the black to remind myself. I think it's T. Yeah. Okay, fine, made it. Okay, now I have a solution of the systems oscillator, of the Bath oscillators, written entirely as a variable of the system variable. So I have literally integrated out the Bath. By integrated out here, I mean I solved the integrated equation of motion of the Bath so that I can plug this solution back into my equations of motion for the systems, right? And if I do that now, I get the following Newton's equation. Okay. So let's look at this equation a little bit more in detail. Oh, it can barely fit the screen, but I hope you can see it. So basically, what this equation has done, what our analysis has done, was to generate an equation of motion, which is still a Newton's equation of motion, but contains additional terms, which are the reflection of having integrated out fast degrees of freedom. We haven't yet assumed the degrees of freedom are fast. Have integrated out harmonic oscillators. And as we observed in the renormalization of the Schrodinger equation example, integrating out unknown physics will generate new terms in the in the remaining Hilbert space, or in this case phase space, right? So we have additional interaction terms which reflect the fact that there is physics intercoupling the systems and the bath. Okay? Okay, it is instructive to reshuffle these equations and write that in a compact notation in the following form. P dot equals negative gradient of u plus sum over alpha c alpha squared mu alpha omega alpha squared. And then I'm going to write this into T naught T ds x of s. I could have used tau. I don't know why I used s. Fine. I'll stick with the notation that I use in the note. Okay, what did I do? I collected all the terms that contain s and brought them into a single parenthesis. Okay, why did I do that? Well, because soon enough we'll discover that these terms will generate friction altogether. And then I collected all the other terms that don't contain s. For instance, you see there's a bunch of them here. Into a term that I collectively called f. Okay? Not very inspiring, just shuffling terms together. And then instead of writing sine, I wrote d by ds of cosine. Once again, why would you like to do that? Well, will become clear in a moment. Well, the second term here can be integrated by part. And we get an equation that looks like this. So I again strongly simplify again the notation, but I'm doing basically nothing but doing notation. Where K is defined by this. And psi is whatever is left which is the complicated sum of q alpha naught c alpha divided by mu alpha omega alpha x t naught cosine plus p alpha naught mu alpha omega alpha sine. Now you find all this formula and the derivation explicitly laid down in the notes, so don't worry too much. And we, basically what we've done is saying c of t is f of t minus mk t minus t naught x of t naught. It's just a matter of collecting terms differently, okay? So the equation that I want to focus for now is this one. This equation here is called, well, let's forget a moment. Let's suppose for a moment, let's ignore this term for a moment. We have a term here which basically couples a force that depends on velocity and is always negative relative to the velocity. What kind of physical effects does this force bring in, according to you?
Friction.
Friction. So what this term is telling me, that if I couple my system to many harmonic oscillator, my system is going to lose energy. Why? Because it will transfer energy to this oscillator, but this oscillator, the chances that this oscillator will coherently, all of them, return the energy to my system, like it's going to be small in principle. But in principle, it's all possible. It's all laid down in here. There are times where this frequency goes to zeros. All this, you have a sum of cosine. For this term to be exactly zero, you would have this cosine to be all zero. But you can, in principle, always have like positive and negative contributions. So that's why up to this moment, dissipation is not really there. Because you have finite amount, and sometimes you get a negative velocity, and sometimes you get a positive velocity. But I would prove that I get a definite arrow of time if I can show that under certain physical condition, this k is basically positive. Right? That's what I need to prove to show that I have dissipation. And if I have dissipation, I have broken time invariance, right? So I have not yet proven that I broken time invariance unless I do the next step, that is to show that this kt effectively for the physical system, at least I'm interested in, is predominantly positive. Okay? And here comes where renormalization group ideas come back to play. Because you see, what this is all about is basically a collection of infinite collection of cosines. So it's basically a Fourier series. And if you really were to, if you were to ask yourself what kind of in Fourier space, how does this look like? It looks like a collection of delta functions, because you know that a phase in Fourier space is a delta function. A phase contains sine and cosine. So simply cosine is a delta function with opposite signs in the real and imaginary axis, but it's still a delta function. And if you're interested in spectral density for positive frequencies, you get only the positive contributions. So in Fourier space, this function here, the k, if I were to look the k in Fourier space, it looks like a collection of delta function. I've given each of these peak a different height because if I regularize the delta functions, assuming I regularize it by the same amount, I get sensitive to the contribution of the prefactors. Where are the prefactors? So it depends very much on how much each oscillator is coupled to my system. Some are more coupled, some are less coupled, and then I get different heights, okay? Now, let's assume for a moment that I get infinitely many harmonic oscillators, so many that I don't have to worry about the fact that this is a discrete sum of delta functions anymore. Now, if I perform the limit, the thermodynamic limit, I can move from discrete series to continuum function, right? And talk about not Fourier series, but Fourier transform, right? So here is where I use the thermodynamic limit. That's ingredient number one for having breaking. Remember, to break time invariance, you need to couple the system to a larger system so that the probability to come back is 0. If your system you're coupling is infinite, the chances that all of your infinite degrees of freedom will all of a sudden go back and change their mind and give back all of the energy at once is going to be 0, right? So the way this is reflected in this calculation is that here I'm taking a thermodynamic limit and transforming a discrete series of delta function into a continuous function. And the next step I'm going to do is going to say, but let's go back here. I'm interested only in the slow dynamics. So I'm assuming, so what you see here is the characteristic response time, also known as memory. Of your system. So think about this in the opposite limit. Suppose I couple myself to a single harmonic oscillator, a big pendulum. I throw the pendulum at time t, I get distracted by my kid, and some second after, the Foucault pendulum hits me. Boom. There is a characteristic response time of my system with the interaction with myself, which is of the scale of omega, right, to the -1. I experiences the effect of my initial interactions after a time that is 1 over omega, right? Now, similarly, whenever you have a collection of harmonic oscillator or in general an open system, you interact with the system will have a finite response time before you can hear it. These are typical concepts in many-body theory. You have it also in quantum many-body theory. It's called the retardation propagator, right? So all the information of the intrinsic dynamics of the response is included in how the system reacts to you. And this is predominantly dominated by physics at the time scales intrinsic of the system. Now we use the hypothesis that the system has an intrinsic dynamics much faster than the dynamics I'm interested in studying for my system. If I'm looking at the protein in water, the water surrounding itself decorrelates on a time scale of the order of a few fractions of picoseconds, while the process that I'm interested in may take 9 milliseconds to occur. Or I say nanoseconds for elementary processes. Okay? So what does it mean? That if I can do the usual trick, go to Fourier space, look at the propagator in Fourier space, and Fourier transform it, and Taylor expand it. Now I'm keeping the linear term. I'm keeping the linear term because I don't want time invariance. I know I want to be sensitive to time breaking. If I had only the second term, then of course time would be coming to with any sign. So, and I can go higher order. I will truncate it here. When I anti-Fourier transform this, it means that my k of t will be a k naught delta function, negative I d by dt delta function, sorry, k1, negative I, k1, d by dt of delta function. And so on and so forth. Now forget about this for a moment. You don't need it. You can stick to the very, very, very basic lowest order term. If you plug it in, then your equation becomes, first of all, the K-naught coefficient is positive because what you're referring to, the K-naught coefficients come from the zero frequency limit of this cosine. So you're sensitive to this coefficient. So K-naught is positive, and if you put it there, you get a P-naught is equal to negative d by dx u negative. Now, if you choose, you can choose K-naught to be, K-naught equal gamma half for simplicity or whatever. Or we already put the half there somewhere. No, I think we haven't. But anyway, if you choose, or 2 gamma, sorry, then you get an equation out, which is the following. You have generated now a friction equation. This is the friction coefficient. There we go. Time has been violated by assuming decoupling of timescales and a thermodynamic limit. Now, we are left with a stochastic, with this force psi. And this requires a little discussion. And since I already exceeded my time here, let me just finish by putting here this term. So remember, if I put my particle in a heat bath at a given temperature, I expect the system to thermalize to that temperature. If there was only this term, the friction coefficient, my system would only lose energy and ultimately reach the absolute zero temperature because it's going to freeze, right? Now, this term here is responsible for the energy you gain by being coupled to the system. So this is an energy responsible for the flow out of energy. And this is for the inflow or outflow. And this is for the inflow of energy. And we will see in a moment that this term will be stochastic in nature, providing the uncertainty phenomenology we were mentioning at the beginning of the lecture. But I think there's no point to rush here. Let's do it on Thursday. Okay? Because I know some of you had to leave at 6, right? Is still here, the person who needs to leave? 4 minutes late. We almost did it.
Yep.
Okay, good. So nothing to add here. You find more details in the notes, but nothing really important. Everything that I needed to tell you is here. We'll keep on going next week, next lecture. Okay. See you guys.
Thank you. Bye.
Bye bye.